It is the 19th of January, 2018, and this is episode 86 of the Unseen Podcast. This is your host, Paul Carr, and I have quite a large panel joining me tonight. For the first time ever, Jon Eckberg. Say hello, Jon.
Hello, Jon.
Oh, come on. Do better. That's a cliche. Say hello, Jon.
Hello, folks.
That's better. All right. And Buckfield. Okay. Buck doesn't care. All right. And Nick Nielsen. Can anyone hear me? Mike Bohler? You there?
Yeah, I'm here. Everything went silent all of a sudden. I'm dead.
All right. Well, Buckfield, say hello.
Hello, Paul. Thanks for having me on Unseen Podcast.
Thank you. That's much better. Nick Nielsen.
Hello, Paul. Hello, Unseen Podcast.
And Patrick Festa.
Hello again. Surprise, surprise.
Okay. Now, let me just preface this. I promise I'll keep the sermon less than 20 minutes. What we try to do with each episode of the Unseen Podcast is have a detailed discussion of what we're going to talk about, starting about a month before the podcast is meant to be recorded. And the hope is that by, say, a week or so before, we converge on a topic. And then we start sort of fleshing out what we're going to, what the details are, and we argue about various things. That didn't really happen this time. And really only Buck, Jon, and I were involved in that discussion. So what I decided to do at the last minute tonight, when we were having technical difficulties getting Jon on, was just invite everybody who replied yes or maybe to the invitation. And so that's why we have the six of us. Okay. So anyway, what I'd like to, I think, since it's Jon's first time here, I'm going to let him kind of have a little extra privilege in terms of determining what the topic is. And he was interested in the Drake equation and how, and this is something that I'm struggling with, so I'm going to let him tell you how the discovery of Oumuamua is related to that. So, Jon, take it away.
Okay, thank you. So I saw a talk by David Jewett on YouTube. He was speaking at an observatory. I don't remember at the moment which one. I'd assigned all of you homework, and you were all supposed to help me remember some of these facts. But I thought I'd be provocative and try to throw out the notion that this one observation of our interstellar asteroid, well, it's not ours anymore, it's long gone, should change a lot of things we thought we understood sort of about our galactic neighborhood. And I guess to narrow it down, I said it would change some terms of the Drake equation. And I think I even said most of them, if not all. So I think if I just take a rhetorical stance, I can stick up for the fact about how most of these terms would change. I'm reminding myself of what they are. There's 7 terms, of course. And, even I hope we all know that the Drake equation, it's not a mathematically or physically derived equation. It's a rule of thumb. That was sort of a back of the envelope.
Well, it's actually a kind of it's analogous to some other equations in other areas of physics, where you look at sort of the source creation rate versus and you sort of the rate at which that is filtered out. There are nuclear physics equations that are quite similar. So it was. I'm sure that when Drake came up with it in 1960, he was drawing from his education in physics. But nobody's ever really said, let me put it this way. It's an attempt to roughly estimate, and I do emphasize roughly, and I do emphasize the word estimate, the number of civilizations in our own galaxy that we could potentially have contact with. And that's all it is. It's not right. You're right. It's an equate, but over the years it stood up because its logic is actually quite sound. Do you disagree with that?
I don't disagree with that. I mean, it's not a, like I said, it's not a strict derivation. It's not what we usually expect to see in a lot of physics. There's no calculus or differential equations involved. It's just, he basically divided up the problem into 7 parameters. And we try to understand, I guess, the 7 parameters as well as we can individually, and then synthesize that into a rough idea of how many neighbors we have in the Milky Way.
Right. Well, you don't need to use the word synthesize. Multiply will suffice, right?
Sure.
I have a question, if I can. John,
Yeah, go ahead.
I don't know about this asteroid that was found or whatever. And can you brief me on it and tell me how it affects your idea of the drug?
That's what I'm trying to get to. I don't understand how it affects it either, but I'll let John continue.
Okay. Well, seeing as how nobody did their homework, I guess I'll have to lecture you all a little bit. So apparently, asteroid Oumuamua came through our solar system. It's currently on its way out, but it came into our solar system with a hyperbolic velocity from elsewhere, and that meant that at no point was it probably ever bound by the sun gravitationally. It came from somewhere else with enough velocity to leave. And so it whatever its history was, it probably had nothing to do with our solar system.
That's true.
That doesn't mean it's unique. Apparently, if we're seeing one, there must be more of these out there. And so the idea was, and David Jewett from UCLA, he's a well-known astronomer for asteroids and near-Earth objects. He sort of made a quick calculation with this one data point and the sort of chance that, I believe it was seen by NeoWise, which is a...
no, it was actually first seen by Pan-STARRS, which is a ground-based...
Oh, that's right, Pan-STARRS. But basically, he said his calculation showed that if we see this one, given the sensitivity of Pan-STARRS and the amount of time that it would have been visible, then basically there should be about 10,000 of these in our solar system, passing through our solar system at any one time, and that's within the orbit of Neptune.
Yeah, makes sense.
So
it's a reasonable inference.
So there's a lot of unaccounted for material kind of passing through our solar system at any one time.
Yes, and is that surprising?
Well, given that it was something we didn't know last October, or at least we didn't have the data to show, I think it is somewhat surprising. Yeah. Okay.
So how does that? Okay. Now, I personally am not surprised. I was wondering why he hadn't detected one yet, because there's lots of driftwood out there in the galaxy. I guess this one was just big enough and came close enough, but and I without having seen the details of Jewett's equation, Jewett's calculation, I kind of suspect it's a reasonable inference from, based upon, assuming it's discovery bias, why we're seeing this first one, and not that there's, that there's only the very first one that ever came through, which is not a reasonable assumption, I think. Because we see discovery bias all the time in astronomy, right? I mean, for example, the first exoplanets that were discovered were the big ones that were close to their stars because they're the ones that created the biggest radial velocity excursions, right? So if you take the first few exoplanet discoveries, you say, oh my gosh, all the exoplanets out there are huge and they're orbiting really close to their star. Well, not really. That's not what it turned out to be. It just turned out to be that those are the easy ones to see. So we see discovery bias all the time. Astronomers are pretty sophisticated about accounting for it, since they've been seeing it for generations. But, for example, you see supernovas from across the universe. But so we know a lot about supernovas, but we don't know that much. We don't know that much about stars that are 1,000 light years away, because they're, there's so many of them. We just haven't had time to study them all. So that's, I think, again, just out of respect for Jewett, knowing that he's not a fool, I would think that that's a reasonable calculation. It's probably wrong, but that's how science works, right? You put out something, you say, this is the reasonable inference from that, and it's wrong, but let's get some more data and we'll find out what the truth is, right?
Yeah, that's an absolutely fair statement, and I agree entirely with it. I just think, his job's to be a little provocative and to inspire new and different ways of thinking. So he's taking his one data point and he's saying, this could be the one thing that tells us a lot about our galactic neighborhood.
He's making reasonable extrapolations.
Yeah, I would say an inference, but yeah.
Oh, there you go.
And we don't know the real population of these things. But what Oumuamua does tell us, in my view, is that there is a population out there. We don't know its statistics in detail, but given our discovery, what we understand about our discovery bias, there probably are more of them. And I would say almost certainly there are more of them that fly through our solar system without us detecting them, because they don't come close enough to the sun, or because they don't come close enough to us, or we just aren't looking in the right direction at the right time. Because if you study, where our powerful telescopes that are powerful enough to see faint objects are looking at any given time, it's a very tiny part of the sky. Now they keep moving around, and Pan-STARRS is one of the ones that is constantly doing surveys, so they have a better chance of catching it. That's why they're building these newer ones that are huge and are going to be able to do more surveys more frequently of fainter objects. I do believe we're going to catch more Oumuamuas in the future. It was interesting, though, to think that Oumuamua, when it came through, a lot of people said, oh my gosh, the light curve of this thing varies so widely over time. It must be some very, very thin cylindrical thing tumbling, which, it should be tumbling about its major axis. Physically, that makes more sense. So it's this long cylindrical thing tumbling, and my gosh, why did it get so long and skinny? It's cigar shaped is what I think the media used. We don't have examples of our asteroids in our own solar system that are that. Well, we have some that are almost that long and skinny, but not that quite that long.
How fast was it tumbling?
What was it? A few hours. I can't remember the exact We could look it up, but it's been carefully measured. I think it's on the order of about 10 hours.
Yeah, 8 hours is what I saw.
Yeah.
And the size?
A few hundred meters, maybe. The size is degenerate with its albedo and its, color and all these other things. It's really hard to estimate all these things together at the same time.
Yeah.
There's been somebody did spectroscopy. I think maybe I saw it in the same talk by David Jewett, but
there has been spectroscopy. Yes, there's been some pretty good work done in that. Yeah.
But it sort of matches what we see in our solar system in the Jupiter's Trojan population of asteroids around its Lagrange points. So it's not as red. It's not as red as the stuff we see in the outer solar system. It's more like Jupiter's Trojans, spectroscopically.
Well, yeah, and it's interesting that we don't really know, we don't know where it came from. We don't know what its parent body was or how it got broken up. And that's an interesting thing to think about. It could have been the result of a supernova that blew up a planet. It could be lots of things. It could be a collision product. Because we see all these processes all going on all over the universe, but we don't really know what kind of pieces they create. We know, they create dust. We see that. But, that's because we see huge clouds of dust. They know they create gas. We see huge clouds of gas, but we don't really know, the bigger chunks, what they look like. This is the first time we've had a chance to look at one. As far as we know, and it may be wrong, it's fairly, it was something that was ejected from some other gravity well that was, that was potentially the result of a collision or a breakup or a stellar explosion. So, until we see more of them, we're not going to really understand the details. We'll never see that one again.
A little off the subject. I saw a report. I think it was a post on Google from one of the astronomy circles on Google. There was a meteorite found that didn't fit the composition of our solar system's makeup. In other words, they're saying that this came from outside the solar system. So there's more of that stuff, perhaps that even reached the planet, as meteors.
That's a pretty chancy conclusion because there's so many different types of meteorites.
Well, yeah. The thing is, it didn't match. And forgive me for not doing the homework on this. Like I said, I wasn't even supposed to be here tonight, but it just reminded me, because you're talking about extrasolar asteroids and stuff. It reminded me of the story that I remember seeing a few weeks ago. The details I don't remember, but it was, they did did various chemical tests on it and found that it was different in some way, some appreciable way than the stuff they would expect to come from our own solar system. So
right.
they're speculating that it came from outside our solar system. So it's a similar story where only this time this thing reached us instead of.
That's the sort of thing that the scientists got to argue about for many years before they.
Well, yeah, but I'm just making
people will put out a study saying, "Oh, look at this," and it's different, and then somebody else will come up and say, "Well, it's not that different," and then back and forth.
Well, I'm just comparing the idea that this is a there's more out there. Like you're saying, there's more out there.
Well, first of all, here's my general warning to everyone: ignore the press releases. Because
this was from it wasn't a press release. It was one of those groups or
yeah, but where's the source?
Or video channels, science video channels, or something like. I don't remember exactly, but it was a post from the astronomers, with the idea that this looks like they didn't say it. Well, they said it looks like it came from outside the solar system.
What you typically see are two things, right? Well, three things. You have a few scientists who are willing to blog about things or explain things to the general public. And this video that John was talking about by by Jewett may be one of those things. But you have formal papers by scientists where they discuss in detail their methods and procedures and conclusions. And if you don't, and let's face it, most of us aren't going to follow the methods sections very well. But you can go to the abstract and go to the conclusions. You can pretty much figure out what the paper's about. And then there's the press releases, and the press releases are garbage.
Actually,
don't even ignore them at all costs.
I remember a small detail. I think they dated it as well, and it dated earlier than the solar system's age.
I haven't seen that. Can you provide us a link?
I like I said, I wasn't even supposed to be here tonight, so I didn't have any. If I was going to be here tonight, I would have had some more detail. But
what is it about the press release process that makes them garbage?
Well, it's the people who write press releases are people who are paid to write press releases. That's their job.
Press release.
They are not. They are PR people working for universities and other institutions, and they are trying to bring attention and public
awareness
of their institution. They do not give a shit whether it is accurate.
It would be nice if it were. That would be a plus.
They were discussing the contents, the metals. What do they call those meteorites? There's different types of meteorites. It wasn't any of those. It was something different, and it was older.
Well, there's lots of different types of meteorites. There's many different types.
Yeah. So I mean, like
because
I said,
they come from parent bodies, right? I mean, it makes sense. There should be different types.
I wish I was more prepared, but I wasn't even supposed to be here tonight. So
there's a bias towards the iron meteorites because those are easy to find. You find them with a magnet, right? But there's lots of other that are not magnetic that look just like rocks.
Yeah.
And if you're not an expert, you won't recognize it's a meteorite. You walk right past it.
Well, the nickel and iron both.
Yeah, there's nickel iron, and the iron is magnetic. And if you have a strong magnet, you'll be able to pick it up.
Nickel is magnetic too.
Yeah, well, you can pick up a meteorite. Those are the class of meteorites you can pick with a magnet.
Right.
And if you watch meteorite people going through the field, they have a stick. They have a stick. On the end of the stick is a strong magnet. They're going to find.
I seen a show that they drag a big thing behind their pickup truck.
Yeah, well, it's called meteorite men. Is that what I'm talking? Yeah, they will find lots of magnetic meteorites that way. They will not find the more silicate type things or the other types of meteorites.
Well, I didn't want to dwell on it. I just wanted to give the comparison, like we're talking about an asteroid that was outside the solar system. And it reminded me of the story, or not story, but it reminded me of the post I read about a possible meteorite that was found that looked like it was.
Okay. We got that. All right. John, let's go back to what you were talking about. Now, I'm curious as to why you think Oumuamua has any impact on the Drake equation at all.
Okay. Well, I brought up the Drake equation Wikipedia page, and there it is, 7 terms. Mm-hmm. We can go through them one by one.
Okay.
If you want. I mean, I think it's going to affect a few of them a lot more.
Start with the first one.
Okay. The first term is R star, and that is the average rate of star formations in our galaxy.
How is that affected by Oumuamua?
Well, it's not affected by Oumuamua.
Okay,
directly.
Let's move on to the second one then. What's the second term?
No, here's what I'm saying. Our understanding of that number did not incorporate the fact that we know that there's basically a whole population of Oumuamuas out there at any one time.
That's true, but why is that affected by it?
I'm thinking the first term isn't so much.
Okay, let's move on to the second term.
The fraction of stars that have planets.
Okay.
Now, this sort of permeating gas of asteroids that's going everywhere, I guess if you build a solar system and you assume everything that the solar system is made out of is sort of stuck to this accretion disk, then that's a very different calculation than if that accretion disk is constantly getting, I don't know if bombarded is the right term, but it's sort of getting interpenetrated by this other gas of galactic asteroidal material.
Well, no, but that's a very, very tiny flux, right? So and not only that, but we already have very good measurements of how many planets have how many stars have planets, and I would think you'll find almost every astronomer out there would think that term is 1.0. Right, so we can move on to the third term.
Okay, fair enough. Stars that have planets, the average number of planets that can potentially support life.
Fourth term.
Let's stay on 3 for a second. These materials are sort of baked by whatever the radiation environment is in the interstellar medium.
Yeah, a little bit, but that's probably not that very important.
The
radiation environment in the interstellar medium is not that big.
But they're going to have a very evolved crust, is the thing.
Yeah.
And they're constantly, so anyway, you're going to have very evolved sort of organic materials on the crust of these. So they're going to deliver a lot of stuff that.
But no, the third term is not, does life start there? The third term is it habitable?
Can they potentially support life?
Potentially support life.
Yeah, I think you can make a case, and that's what I'm trying to do here. I'm not, I'm not investing my future on this Drake equation. I'm not going to write a book on it. I'm just saying, I'll sit up here and try to rhetorically make the case that this should change some things for us.
Why? Still on the third term?
All right. Let's go to 4.
Okay.
The fraction of those planets that actually develop life.
Okay.
Again, it might not be a large effect, but the thing is, persistent small effects can have big consequences over time.
Well, but we already know that within our solar system, there's lots of organics. So, how would that be an even important effect at all?
Well, if it ratchets it up another level. If there are a large number, even over as he just noted, over a long period of time, we're talking billions of years, but that's a appropriate scale for cosmology. But if we've got these rocks passing between planetary systems on an interstellar scale, then you could have a higher likelihood of a panspermia on an interstellar scale that passes through the life in one planetary system, and it goes in the following 10 to 100 million years, it passes that life around to a few dozen other planetary systems. You could have panspermia on an interstellar scale.
Okay, panspermia is a different subject, but yes, I recognize that. If you think these rocks might be actually harboring microorganisms, or the spores of microorganisms, then that would be some kind of that's a different game. That's a game changer, right? But there's very little probability that any of these rocks will hit anything that might be habitable, and B, there's a very low probability that they're actually life-bearing, right? We really don't know those probabilities, but we expect them to be very low.
Yeah, but if over cosmological scales of time, you'd only have to have, say there are billions and billions of these Oumuamua kind of space rocks flying around interstellar space.
Yeah.
But say
I'm sure there are.
A tiny portion of 1% of 1% bear simple forms of life, and maybe you happen to get one that's so constituted that it's always sloughing off layers of life, especially when it goes to the gravitational field of another planetary system. So say you've got a planetary system that's got just the perfect planet in just the right place, and it's got, but it's sterile. And the Oumuamua kind of asteroid with life comes through, sloughs off a layer of its organic material. It gets drawn into the gravity of that planet, and it goes from being sterile.
Well, it'd have to get really close to slough off anything. I mean, it'd have to come like basically hit it. I mean, because most planets are, the Roche limit is tiny, so you'd have to go. It'd be after a really big planet, and the really big planets are gas giants. Right. So.
Well, if you had an interstellar object that, like a comet, when it got close to a star and started to warm up, and then boil off an outer layer and create a tail, then that tail would be an opportunity to spread whatever microorganisms would be on the rock.
That's sort of what I was thinking. It was, it sprays off a bunch of, crystals or gas.
Well,
and
they're
eventually a planet drifts
small dust
across
particles for the most part, and
yeah,
a little, and the gas is not relevant, but yeah, I mean, there are little bits of dust that could fall if it comes very close to the host star. Now Oumuamua did come pretty close, and it got quite hot on the outside. But that's
what is quite hot. What was was there a measured temperature on the surface?
I can't remember. I think it rose like I'm not actually. I don't trust my memory right at the moment, but I think it rose like 100 degrees C or something from. It rose to where you could have had volatiles coming off.
Well,
and they did not see volatiles coming off of it, which suggests that it's not ice on the outside.
As far as I know, it didn't develop a coma.
No, which suggests there's a crust on the outside that is keeping whatever volatiles are there contained, and thermally insulated, so they don't pop out. Now, if a comet come close to the sun, whatever volatiles are on the surface or near the surface of the comet will start popping off all over the place, and forming not only gas but dust trails, and you'll see a pretty dramatic dust trail in some cases. In fact, in most cases, you get a dust trail, and you get also an ion trail where the gas gets ionized when it comes close to the sun. We have satellites that image sun grazer comets all the time, and it's just gotten routine. So many of them that they're not individually studied anymore. But you can get, if you come close to the host star, you can get material volatilizing off the surface. Yes, that can happen. And that's where we get some of our meteorites from comets that are popping off bits and pieces as they come close to the sun.
Haven't we had a few meteor showers that were the result of that in the past few years?
Yes. Well, yes. Some of them are pretty well traced back to specific comets, and my memory's failing me on which ones, but there are known comet showers, meteor showers that. Now, when this meteor hits the atmosphere, it's typically a very, very tiny. It's maybe a millimeter in size, and it goes through extremely high heat. So any life in that particle is going to be completely annihilated. If you have a little bit bigger particle, which you will get occasionally, whatever in the middle of it could possibly survive. There's a tiny statistical tail that you could have survival.
Is it not possible that there's a lot more smaller than a millimeter that we just don't detect?
Well, yeah, there are. Sure. Some of the dust particles are much smaller than a millimeter.
Yeah. So if it was like a collection of a couple hundred organic molecules, it
The
wouldn't.
thing is, if something gets much smaller than, say, a micron, it gets blown out of the solar system in no time.
Just in the wind?
Not in the wind. It's actually the solar radiation pressure.
Okay.
If the solar wind actually has very little effect on it, but it just gets blown out because it's so fluffy that it just, it's gone. There's a size of dust particle, say bigger than a micron or so, that will stick around for a while and could hit the Earth, and you might even see it if it on a dark night if it hits the atmosphere.
Wow. A micron.
Well, no, bigger than a micron, maybe 100 microns.
Oh.
A millimeter is 1,000 microns for those who are not keeping score at home. So a millimeter is a tiny particle, but it's moving at tens of kilometers per second. So when it hits the atmosphere, it's going to make a bright light.
Okay, so we have some disagreement about that impact on that factor in the Drake equation.
Right. Well, I mean, I think it might bump it slightly one way or the other, but it's not going to change it by a factor of 2. Which a factor.
Does anybody think that it would decrease the chances? I mean, I don't know how it could decrease it. I can see the panspermia opportunity. I can't see any way of it harming the development of life. I suppose I could come up with some very carefully selected example.
How about if we detected a number of interstellar rocks coming through the solar system, we were able to visit them and find them all completely sterile, implying that there is not life elsewhere?
Well, I don't think it would imply that. It would just simply imply that life doesn't survive the interstellar journey.
Well, given what we know about, basic organic chemicals like formaldehyde forming even where there aren't planets or in the interstellar medium, and known to exist quite commonly in the universe. And I think there was somebody who speculated about, carbon-based organic molecules being a sticky surface of Oumuamua.
There's lots of sugar out there.
There's lots of sugar out there. And there's lots of water.
Alcohol.
And there's lots of water, and there's lots of alcohol and petrochemicals. All that stuff is out there. So if rocks came through and we found that they were barren and didn't even have these organic molecules on them, maybe that would influence how we would calculate what becomes of these organic molecules.
That's true. Although I think that would be a surprise, certainly, if there were no.
It would be, and that's why it would be worth taking a look at.
Because comets have organics on them. So
yes,
and asteroids have organics, as far as we can tell. We should have our first. Actually, not our first, but we should have our first really large asteroid sample return in a few years from OSIRIS-REx. We do have one from the Japanese, but it was a very, very small sample. But still, I mean, we can tell from astronomical studies that organics are all over the place out there, and so if we found a rock from another solar system and it didn't have any organics on it, I think that would be a special case. We found lots of them like that. That would probably be disruptive to our understanding.
I'd like to point out that the Drake equation, of course, was from the 60s. And in those days, the first term about how many planets that might be habitable?
The first term is how many stars are forming. I think we do know the answer to that one.
Okay, well, what I'm trying to say is that part of that Drake formula is about the possibly habitable planets or something to that effect. That number has changed drastically since Kepler. and forward.
Well, the first term hasn't changed. No, that's not true. The first term hasn't changed since the mid 20th century.
But I think our understanding of the first term has changed because we no longer we understand the star formation as a process that has already peaked in our universe, and it is running down.
Yeah, but we also know that I mean it's really kind of like more of the average star formation rate over the last several billion years. It's not really just like today's star formation rate.
Is there not part of the equation that asks, how many planets may be habitable, et cetera? So
that's the third term.
Okay, so the third term has been drastically changed.
No,
Yes.
well, I'm seeing the third term as stars that have planets. Oh, the average number. Okay.
Yeah.
That can potentially support it.
Now it's at
And
least
then
one.
it's the one that actually
It's the
goes.
habitability question, which I think we're starting to get a handle on that from all the exoplanet data we have now.
Well, that's just it. The exoplanet data. I mean, the whole thing has changed over the decades.
Yeah, that's true.
Yeah,
And-
the concept of habitability is changing a lot, especially because of the likely prevalence of water worlds and especially subsurface oceans under ice.
When Drake wrote down that equation in 1960 at Green Bank at a seminar where they were discussing, SETI for seriously, it was the only term that we really had a tight handle on was the first one,
Right.
and
Okay.
that hasn't changed much. It's roughly
No,
10,
but I'm talking.
roughly 10 to 20 stars a year. That hasn't changed.
I'm talking about the planets. I'm not talking about the actual.
Yeah, well,
stars.
that we didn't. And when Drake wrote them down, we didn't know the second term, which is how many stars have planets. We had
Right.
and we had never detected an exoplanet at that point.
And also how many planets each star has. I think the number is actually on the average 1.2. So I mean,
Well, we now think that every star has planets and probably has 2 or 3 planets.
right.
But
at
the
an average.
observation of selection effect is still with us.
Yeah, but
because if
the statistics are starting to pile up, and it's getting too hard to deny them.
Right. But if we got a close-up view we'd probably see a lot of dwarf planets that we can't see yet with the current.
Oh yeah, well, we have a couple of missions coming up. TESS will launch this year, hopefully. It's on track. TESS is NASA's Planet Explorer, which is meant to look at closer stars and will cover a wider range of the sky. And then the Europeans are working on something called Plato, which will cover also nearby stars and look for sun-like stars. And so we'll have better statistics in a few years, but I think the Kepler statistics are very hard to deny. They're
also
it's going to be a tweak. It's not going to be a total turnover of that.
They're also doing something that I've been nagging about. I just watched a weekly space hangout with Tony Darnell. They're looking at K stars now.
Yeah. Well, K stars have potential. Yeah.
Yeah.
But that's
my opinion. Always my opinion was much better than M stars, is what I always said.
well,
And possibly even better than G.
we don't know that, but
That was what I've been.
the compelling truth there is that there's a lot of them.
Right. There's more than G, which our sun is.
There's a lot of K and M stars out there, and most stars are small red stars, and something like 70% of them. So
Right. But the problems with the M-class stars, we don't have to go into all those problems that might have, planets too close to them but the K stars, not only is there much more of them than G, but there's also that they're not so tiny that the habitable zone is so close.
well, yeah, but I mean, they're still pretty close.
But are they are they far enough away that they're less likely to be tidally locked to their host
Less
star?
likely, but they can still be
Right.
entirely locked.
In other words, if it's a better build, in my opinion, if it's a better build than an M-class star.
Well, we don't really know. I mean, opinions aside,
I
we
did
don't. We
say-
just don't know.
Well, in the same way we didn't know before Kepler about the frequency of
Local
planets,
hangout
but there were
was-
certainly many people who thought that most stars had planets, which is
Yeah.
now seems
Well,
to
the
be the
weekly
case.
hangout was the subject was the case for case day class stars. The
Yeah. Well,
habitability.
the thing is with Kepler, Kepler was fantastic. It did a lot of great statistics, but Kepler's looking at stars that are quite far away, for the most on average, and a very small patch of the sky, relatively speaking. And so Kepler discovered had a bias towards larger planets and also shorter period planets. And the problem is that Kepler did not live long enough to see a planet with a 2-year
right.
period repeat 3 times. Which
And also, it was specifically a transiting.
transit is what transit method is what we're talking about here. TESS will also be transit. Plato will also be transit. Now, and the transit probabilities are low, but it's statistics, right? Yeah. If you look at 10,000 stars and find 100 planets, well, that means there's a lot more planets out there because the transit probability was low enough, and it's easy to calculate the transit probability. That's an undergraduate geometry
that's what I'm
problem.
saying. In other words, the fact that we're looking at transits mostly.
Yeah.
Well, the chances of having a planet transiting, in our field of view, is far less than the number of stars out there.
Microscopic.
Yeah.
Well, it's a few
How many are
percent.
face on? And the only way
I wouldn't say microscopic. It's a few percent, depending on the size of the star. The smaller stars have smaller transit probabilities. So, for the same distance, but for the same habitability, it's roughly the same. So, because the planet has to be in closer, right? So,
Right.
And
the farther the planet is away from the star, the lower the transit probability.
Yeah. Well, the general idea that I'm trying to point out here is that not only is there stars out there that are not facing edge on to us, as far as the orbitable plane of its planets, but now we know that it's likely that every single star has some planet around it.
Yeah, I think we do know that. Now, not all those planets are likely to be habitable, but we do know that they have planets.
That's a big difference from what we thought in 1960s.
Yeah, and there are papers out there. I'll try to find some links for you that estimate the fraction of those planets that are habitable, and it's around 10%. Most people come in like between 5 and 20%. And I know Jill Tarter led a group that a few years ago that did an estimate based on the statistics that they had then, that came in with like 5% of red dwarfs had habitable planets. The real number is probably roughly around 10%. And if we're as close as a factor of 2, I'm happy, because that's about as good as the Drake equation is going to get. Okay, let's move on to what is the fifth term of the Drake equation.
Well,
Intelligent civilized life.
Yeah, I've been staring at the equation here for a second. I think there's sort of a built-in bias. The discussion of panspermia, I think that's a good one, because at least the way I see it's written here, it assumes that life develops on the planet itself.
No, it actually doesn't assume that. It just assumes that life arises on that planet.
Well, that's the same thing, isn't it?
No.
What's the difference? Yeah.
No, it's not the same thing.
Okay.
If panspermia affects that, then you can account for it there in that term.
Okay.
Oh, fair enough.
Tomato.
Well,
No, it's true. We don't
actually
we
develop
don't, we,
life, and if you include in development this panspermia, yeah, that's legit.
Here's the interesting thing. This is very recent. And again, I don't have a reference that I can share with you off the top of my head, but there's a lot more evidence that life on Earth developed very, very early, about as early as it possibly could have, given all the bombardments we were under. And that does, and I had this conversation with David Grinspoon 5 years ago. That does suggest that it didn't come from here, that it may have come from somewhere else. It doesn't prove it. It does raise the possibility that maybe Mars had life first, or maybe Venus had life first, and it made its way over here. And if it took 20 million years to get here, that's nothing on that time scale. Right?
Yeah.
I mean, that's one interpretation.
Yeah.
I'm trying to get a feel for the culture of your show here, and I don't want to butt in too much, but the other assumption, I guess, that you could make about an early life arisal would be that life is an unavoidable consequence of thermodynamics.
Mm-hmm.
And that case has been made fairly recently using some statistical physics.
Yeah, and I think there's actually some pretty good arguments, although I'm not a chemist. I don't know if Patrick, you're on. There's two Patricks.
Yeah, I got an error 32, and I got kicked out, and then I said try again, and I said
Okay, well I'll kick out the old one. Okay, you're now you're here. Okay, all right.
Did you kick out Patrick or his evil twin?
I kicked out Patrick's. I kicked out the one with the goatee and the evil smile.
That was weird. Error 32.
It was a transporter accident, Patrick. It's all right.
Okay.
All right.
All right.
Sorry, John. Go ahead.
Oh, no problem. So I guess term 5, which is the fraction of planets bearing life on which intelligent, civilized life has developed. You can make the case we haven't seen any proof that this exists yet. But
especially since the election.
If we take,
well,
if
yes,
we take
we used to think there was at least one planet, but now we're questioning that.
Yeah, there's still hope for Mars, though. So if we take our own planet as an example, this happened relatively quickly on a geological or astrological timescale.
Well, now wait a minute.
So,
that was it took about 4.5 billion years out of 4.5 billion years. I mean, we've been the technological.
The blink of an eye.
Doesn't this account for, this isn't just life, this is intelligent, civilized life.
Right. Technological civilization. Let's put it that way.
So does that include agriculture? Is that the marker? What's the marker for technological?
Radios. Being able to build a radio. Building a radio.
Okay. Not taming of fire that's detectable.
Well, but on time scales, the taming of fire was only about 1 million years ago. That's nothing compared to 4.5 billion years.
Carl Sagan
to agriculture.
Agriculture is only 10,000 years ago. That's nothing. That's a blink of an eye.
I mean, I think
Carl Sagan often used the construction of radio telescopes as his measure.
I think that's not a bad benchmark, actually.
I think that's down in term 7, though. We're still on 5.
No, 7 is different.
Okay, maybe
7 is how long you can do that.
Yeah.
So I mean, I think you can make the case that Earth impacts have affected civilizations in the past, and I won't try to do that here. But I don't think that this population, unless it can annihilate a significant fraction of these civilized planets, I think the effect I'm talking about would be small on this, on term 5.
Yeah, I agree.
And that's mostly due to the fact that that's going to be a fairly short time period.
What? This is a fraction of planets. What do you mean by short time period?
Well, I'm saying, using our own civilization as an example, we're talking about a time period of about 10,000 years.
Yeah.
That the life-bearing planet developed a civilization.
Yeah, but the life that you're talking about, the period from the origin of life to the emergence of technological civilization, which is probably 3.5 billion years.
No, in that I think what you just mentioned is comes from term 4.
No, the term 4 is, does it develop life? That could be microbes 4 billion years ago. Right?
Sure.
So complex life is a completely, and now what buried in that 5th term is a whole lot of evolution from microbial life to complex life to life on land to life that manipulates its environment for its own purposes to life that is that can build a radio telescope. The complex life on land to radio telescope is another blink of an eye. It's a couple 100 million years, right?
Does that count as communication, the radio telescope?
Well, it's communication, I suppose, but it's more just the ability to build one, which requires a whole lot of other biological development. Okay,
because that does seem like you're mixing 5 and 6.
No, communication is different. If a radio telescope means that you're aware of there's a bigger universe, and you have the ability to make nuanced detection of its properties. We went from knowing that there was electromagnetism to Maxwell's equations in about 100 years, and another 60, 70 years to building radio telescopes, largely driven by World War II, but maybe 80 years, but still, again, a twinkling of an eye, just nothing in terms of time.
So, but are we saying that Sagan's criteria applies to 5 or 6 primarily?
5. Technological civilization. How do you define a technological civilization? Well, you define it operationally by what they can do, right? Agriculture doesn't count, although it is
pyramids. Cities.
I think you can make a clear case for metallurgy as a technological civilization.
Well, yeah, you can make a case for a number of things, but you have to put a line in the sand and say, okay, if they get to this point, then it counts on term 5.
To me, a radio telescope is a listening device, and listening is part of communications.
Well, yeah, but it's not the whole story.
No, but
it's not the whole story.
Communications has to go both ways.
It is the line in the sand that you pointed to, and I think that we can say, to me, that's a lot. I don't know. It seems more like developed communications. It says technologies that really. Oh, this is transmission. I guess radio telescopes.
Well, no,
are pretty easily convertible into. Well,
you're going to develop transmission and reception at the same time, and they're two sides of the exact same coin.
Okay.
But
to me, it seems more friendly to 6.
But the term 6 is really more about your willingness,
broadcast.
Yeah. It's term 5 means you have the technology. Term 6 means you use it. Right.
In two different glosses of the Drake equation, I'm looking at one at SETI.org and one on Wikipedia. Both of them just say intelligent life, and they don't specify technological life for term 5, FI.
Yeah, I don't like the term intelligent life because nobody can define that.
Well, you could define it
are octopi intelligent? But we're not going to have. They're not going to build radio telescopes. But are dolphins intelligent?
No. But they have just like a planet that potentially might have life is interesting, but it's distinct from a planet that actually does have life. A planet that can give rise to a complex brain, like you find in mammals, that's very interesting from an astrobiological standpoint, even if those mammals do not develop an abstract intelligence, but they certainly have a basic kind of intelligence.
That's
There's
true.
a big difference between a fungus or a mold and an octopus that can open a jar.
Yes, I agree. And that's why I think the intelligent life is a reasonable distinction, and distinct from developing a technological civilization. Because our own ancestors, if they hadn't have settled down and started digging potatoes, they might have stayed
Big mistake.
They might have stayed in a high level equilibrium trap of hunter-gatherer nomadism, and we might still, might be a million human beings distributed around the planet as hunter-gatherer nomads, and never having made the breakthrough to settled civilization.
Right. Well,
then you'd have intelligent.
Yeah, I had this
intelligent
discussion
life
with
without
Robin
even
Hansen a number of years ago, and he said, yeah, they were pretty happy as hunter-gatherers, but they could be
There are people who have called hunter-gatherers the original affluent society.
but they could be out-reproduced like hell by farmers, and that's why it happened. It's not evolution doesn't make you happy. Evolution makes you reproduce, and so that's why. And every once in a while, you get this revolution where the doubling rate of growth goes from, thousands of years to hundreds of years to tens of years. And, so we've had at least 3 of those revolutions. We've had the agricultural revolution, we've had the industrial revolution, and we had the information revolution. And we're all, and for each generation, at the first few generations at the beginning of each evolution, life is really hard. It doesn't matter. Evolution doesn't care about that. You're gonna beat the shit out of whoever came before you, because you're gonna be able to. You're gonna have so much more wealth than they did. And it does so. That you get this now. Would that happen everywhere? I don't know. I really don't know.
You would expect to see a bell curve. You'd see some very specialized that went immediately into settled agriculture, and some that stayed in the high level equilibrium trap of hunter-gatherer nomadism. And then in the bell curve, you find the bulk of them.
Well, if you had a planet where domestication of plants was not easy for some reason, yeah, I can see that. Or domestication of animals, which followed shortly on the heels of domestication of plants. That was that could happen. We know there are species of animals on this planet that aggressively resist domestication.
Well, look at Jared Diamond's argument in what was his book, Guns, Germs, and Steel, that made such a big impact. And he argues that the east-west orientation of Eurasia made it possible for settled agriculture to become a much bigger thing there, and also the availability of domesticable beasts of burden. Whereas in North and South America, you've got the north to south orientation of the continents, so there's not a whole lot of movement between the various ecosystems at different latitudes. And you didn't have the oryx to be domesticated into cattle. You didn't have the horse. Well, the horse evolved in North America, but it went extinct until it was reintroduced. So you're missing a lot of essential factors that made civilization more effective in the Eastern Hemisphere than the Western Hemisphere. So if you had an alternative planet where you only had, say, a chain of islands, or you had a northwest continental orientation, and you lacked domesticable animals and beasts of burden, that might be a contributing factor to the absence of the emergence of.
It might, but they did have civilization in Central America and South America.
They did, but we don't know if it would have ever achieved an industrial revolution if the Europeans had.
They didn't know what a horse. I mean, when the Spaniards arrived on their horses, they were pretty astonished to see that a man riding on a beast. They didn't know that was possible.
Because you can't ride on a llama, but you can use them for packing.
Yeah.
Ironic.
And also have really, really warm fur, warm wool. But, but I think that, yeah, the main thing about the East-West thing is that it did spread, right? I mean, the use of lots of things spread from east to west across Eurasia, including resistance to diseases, which was the big downfall of people in the New World. They didn't have that resistance, and they just died in droves when the Spaniards arrived.
Diamond Paul calls that the old world disease pool because Europe, Asia, and Africa were constantly transferring their diseases between the various continents, and then the people who had immigrated to the New World were not exposed to them until the Spanish came, and then there were
their population crashed within
about 90%.
Yeah, and so but in terms of would that happen on another planet, I don't know. We don't really know what all the variables are. There might be lots of planets out there with billions of happy octopi that are opening jars but not building radio telescopes.
Yeah, well, that's what I recently wrote about in a blog post called The Waterworld Hypothesis, because there were a couple presentations at a couple different conferences, one right after another, where people prominently discussed the possibility that life is common, even intelligent life is common, but like you say, it's octopi stuck in subsurface oceans, and therefore not because they don't develop a technological civilization because of their aquatic nature.
Yeah, and SETI is not SETI. Well, I should say not interested, but not. SETI is not able to address those kinds of
in its current form. In its current form, it's an embodied selection bias.
Right. You have to have ETs that can build radio telescopes or lasers or something like that can communicate across interstellar distances. Nothing else.
I would point out, though, that you can't have any investigation without some sort of bias toward what it is you're looking for. To make any sort of judgment, you can't have a judgment without some framework in which to do it. So that comes with the territory.
Yeah, I think it does. It doesn't mean that you have to be blind to other possibilities. It just means that your experiments are going to reveal what within some category of thing you're looking for.
More technically, I think it's what we can do.
Before I forget, has anybody heard of this theory that there is no space in terms of like a stage upon which things are put? Like you have some object and you place it in some location of coordinates that exists there before. The idea is that space is like a family. A family doesn't have an actual substance. It's a set of relations between entities.
Well, this goes back to Newton.
Yeah.
This goes back to Newton, and philosophers sometimes call that point of view the container theory of space, that space is an absolute container that you put things in. And
was that Newton and Leibniz that had that debate?
Yeah, Newton, yeah. And there's this great series of letters that were edited by Clark. I can't remember the guy's first name, but there's Newton argued for absolute space and time, and Leibniz argued against it. And just like that, it's just a collection of relationships between objects, and it doesn't exist as any kind of substance or container.
What do you think of that?
What do I personally think of that?
Yeah.
For purposes of science, the relativistic theory of space is pretty much de rigueur. It's the basis upon which relativistic science is done, and probably quantum theory as well. I think that a case can be made for space and time independent of empirical scientific considerations. It's a difficult argument, but there's a great book by W.H. Newton Spitz called The Structure of Time, where he builds on some arguments from Sidney Shoemaker, in which he tries to prove the meaningfulness of empty time. And I've discussed it in some blog posts, and I'm actually working on some more material in relation to that. It's not something that would convince most people because it's very much a philosophical argument and not a scientific argument. And there's also an interesting book that came out, I think, in the late 80s called Physics and the Ultimate Significance of Time. There are a bunch of physicists or philosophically minded physicists who have been influenced by Alfred North Whitehead, who, of course, is well known for process philosophy.
Right.
But this is definitely a minority view. This is the view that I personally have, but I'm well aware that it's not mainstream, not common. But I think the most important thing that you have to qualify this view with is that you can no longer maintain a Newtonian conception of absolute time and space. I mean, that just doesn't work in a relativistic universe. So any theory you have of time that maintains either a temporal realism or a spatial realism or a spatio-temporal realism, which is ultimately what you would want in a relativistic universe, because space and time can't be completely divorced from each other, you would want to make your realist theory of space and time sensitive to the reality of relativity.
Yeah,
and I think that can be done.
Yeah, I mean, Newton's concept, Einstein basically said, we can't have this anymore and still be consistent with physics. And that's the accepted view now. That there's no absolute motion. But the way that space and time are relative is not arbitrary. It's very clearly defined, and that theory is incredibly well verified. So anyone who wants to challenge that needs to deal with the fact that the physics is so good.
Well, what would need to change? I mean, what would be different if Einsteinian space, for lack of a better term, was not a relation of was not a relation that held between objects?
I don't understand your question.
Well, there's this idea in Einsteinian space-time of a stage upon which objects exist. A star exists within this stage that then gets warped in a certain way.
Well, actually, Minkowski was actually the one that came up with space-time, but if you want to be historically accurate, but Einstein's theory really deals with events, not with objects.
Mm-hmm.
Objects are really not important in Einstein's theory.
I'm sorry?
Objects per se are not really that important. And that's why you have events, and so you have quantum field theory, which is this very abstract version of how the universe works, other than gravity, and it doesn't really require some kind of object permanence.
But even aspects of relativity theory are quite abstract. One place Einstein defines a body as something that can't be penetrated by another body, but he's meaning something. His meaning there is something very specific. It's not what we mean in ordinary language when we say one body can't penetrate another body. But that is one definition that is sometimes used for bodies in relativity theory, and it's also. I lost my train of thought. I was going to mention another really abstract thing in Einstein. So, every theory embodies abstractions that are somehow coordinated with empirical data, and every theory embodies invariance. In fact, in his later life, Einstein said he wished he had called relativity theory invariant theory because so many people have been thrown off by calling it relativity theory. Well, so Einstein gave away absolute space and time, but he exchanged for them the absolute speed of light.
Well, it's also the absolute proper time, which is the same in all frames of reference in special relativity. And which is incredibly valuable concept. But you can also, I mean, the notion that, that space is, measured by one frame of reference and measured by another, that's legitimate, but there's a transformation between them that is, and there's a whole bunch of stuff at the Large Hadron Collider that wouldn't work properly if that wasn't correct. It's not just a guess. And in fact, it all started with Maxwell's equations, and trying to put some solid foundation underneath electromagnetism, which is what if Einstein's paper was about, and in 1905, and so I'm not sure I understand your question still, Buck, but the problem is that you've got extraordinarily well verified theories, and both in special and general relativity, and the question that you've got to ask questions about conditions that haven't been tested yet. Which
I think, if I can jump in here,
sure.
Sorry, I'm not used to throwing elbows too hard, and I'm a newcomer, so I didn't want to.
Oh, throw an elbow if you want. That's all right.
Jump in.
I got my mouthpiece in.
I think I understand what Buck's referring to, and it's this concept of that space comes from basically local entanglements. So it's actually a quantum concept, and there was a paper published a couple of years ago by no less a luminary than Sean Carroll, who's sort of a famous.
Yeah. He just came out with a paper in Philosophy of Physics last week.
Sure, but what we're talking about is different layers of description, right?
Yes.
How much formalism, how much math do you need to describe what's happening? And there's the famous, you start with Newtonian, you go down to Einsteinian, and it's not the idea you're talking about doesn't negate everything that's come before. Newtonian physics still works in the solar system for the most part. It's just how far down the rabbit hole can you go to try to explain this in a self-consistent formalism? And so, as a member of a 3D space-time, or a 4D space-time, I guess I should say, I'm completely taken by the illusion, even though we might be holographically encoded on the surface of a singularity somewhere, where, I'm okay with the 3D plus time description, but how far down the rabbit hole do you want to go for ultimately, some practical benefit?
Well, this notion that space-time is emergent from quantum entanglement is an area of active research, and it's not. It really doesn't affect anything we currently know about physics. It exists. This is something that would affect physics at a very, very, at the level of the extremely small. We know that general relativity is an incredibly well verified theory. At the level of the large, it's accurate, and all these work that's going on right now, quite interesting, quite possibly correct, but not a done deal. And none of it really justifies. It doesn't mean, and none of it means that all bets are off.
I'm
trying not to encourage the Richard Hoaglunds of this world to jump in and say, "Oh, look, I got hyperdimensional physics working in my wristwatch" or something like that. Which, believe me, they do talk about stuff like that.
Well, okay. Now you forced me to really thank you again on the podcast for referring me to Oh No with Ross and Carey and their Flat Earther series. especially episode 5 in that series where they talk to that guy who's the real advocate. And he sounded so reasonable. What was that guy's name? I don't even remember. It's in episode 5 on that, where they brought him into the studio and talked to him. And he really seems to think this is the case. One of the things that they had mentioned in an earlier podcast was that a lot of the flat earthers talk about parabolic launches for these spacecraft. And they say, well, NASA launches the thing and it goes up on this parabolic path. And so somewhere out in the ocean, it falls down. The astronauts parachute out or something else, or maybe they're never even on the thing. And it's all this takes place under the dome. And, he sounded like he really believed this was going on. And I would really love to say, hey, come down here to Patagonia and we'll talk about where on the dome the sun would be. And you can have one of your friends in Australia, take some reading and we'll Skype with them and take this reading. You tell me where the sun's going to be on the dome and we'll look at what measurement he should get relative to here and see if they can work it out.
Oh, they have half-assed rationalizations for everything, and it's good enough for them, not for anybody else.
Well, any active science has areas of unknown. If there's nothing unknown within its domain, it's kind of it's kind of like chemistry. I mean, there's not much new chemistry being done. Now it's all pretty much regarded as it can sort of be broken down into physics. And so there's lots of things that this advocate for the flat Earth model, he was very upfront about, well, we don't know this, maybe it's this, or they said, well, the sun, do you think the sun is being projected on the dome? Or do you think it's this thing that's fixed on a track and shining down on us? And he was like, well,
flat earther bullshit?
What's that?
I said, do we really have to talk about the flat earther bullshit?
I find these guys fascinating.
Well, I was starting to say something before, but I don't think it's relevant anymore.
I find them sad and delusional, I have to say.
What I started to say before, I don't know if it's relevant anymore, but before the subject is completely gone, you were talking about the aquatic life and versus, the land life. And I was saying it depends. In other words, what we can look for, what we're able to look for. And we're landlubber creatures who are intelligent, and our technology deals with, radio telescopes and things of this nature. Whereas a completely different type of intelligent life, if it was aquatic, would have a whole technology, if it existed, that we would not even, be able to dream of right now.
Right. Well, that's the sixth term of the Drake equation. It accounts for that, that some fraction of intelligent life might not be able to build radio or be interested in building radio telescopes. Might even not even be aware of astronomy.
Right, but they may have a technology that we are completely oblivious.
But that's possible. Sure.
Then that leads to the question is of like the idea of the panspermia. How much alike is, if say let's just assume that there's life everywhere. How much alike is it, and how much unlike is it? Like, for example, Gene Roddenberry in his Star Trek, there was always this commonality. There was humanoids, whether they had bumps on their head or not, and then there was, different kinds of animals and stuff. But there was a certain likeness.
Yeah, well, I think it was on the movies we discovered that it was all because we had common ancestry or something.
Something to that effect, yeah.
Yeah.
So, that was that Next Generation.
Then is the opposite. Then there's the opposite, who are people, like even some scientists are trying to guess as to what life could be so different on another planet. They got animals floating in the atmosphere and stuff. So in other words, there's, how much alike are we and how much dislike are we? And
well, that's why people have started using the term, life as we know it and life as we don't know it.
Right.
Peter Ward wrote a pretty good book with that, life as we know it or life as we don't know it.
Well, Mr. Spock said that a few times, right? It's life, Jim, but not as we know it, right?
Mm-hmm. Probably.
That Yeah, but that's what the six-term Drake equation does. It divides up the life that would potentially be capable of higher cognitive functions, but not interested in communicating across the universe, and those that do, right? And so I think the Carl Sagan criterion is as good as any I can think of. That is,
Radio telescope.
radio telescopes. If you can build a radio telescope, that means several
That's
things.
our kind of
that means
technology.
you're aware there's an outer universe. You know something about it.
You're in the club.
And speaking of aquatic life, being intelligent, I just heard it on NPR radio. There's a famous, and forgive me for not remembering her name, a woman who studies whales, and she's out in the water a lot. And suddenly, this great, I don't know what kind of whale it was. It was a huge, 40-something foot whale, started to pick her up or move her, and she actually got bruised a bit, pick her up on his nose and stuff. And it turns out, to make a long story short, that there was a shark near her boat, and the whale was actually protecting her, even though the damn thing was so big it hurt her anyway. But the thing could have eaten her, could have just opened his mouth and just swallowed her. But it was actually protecting her. There was this altruism towards a different species of the planet. It was. She has never ever seen anything like. If she said that if somebody told her this story, if it was somebody else, she wouldn't have believed it.
I heard about that.
Saved her life.
I heard about that story that Patrick just related, and a year or two ago there was another absolutely fantastic story with a video with it. You can I'll find the link and send it for the show notes if you want. That shows an elephant seal trying to feed a human diver, and he brings them some I think it's a dead penguin or something, and shoves it in his direction to try to give him some food. It's really remarkable.
Sign of affection.
Or altruism, if you want to call it that.
Or maybe trade. He's offering that in exchange for fish, maybe.
Pro-social behavior.
Yeah.
Pro-social, yes.
Mm-hmm.
What's
Interspecies pro-social behavior.
What's more is there was, I think there was either some dolphins or some other animal, pushing the shark away or attacking the shark, while this whale was trying to protect the woman. There was a fight going on, and it was like, wow,
Yeah, they were, if I remember the story right, they were humpback whales. There were two of them. One of them rolled her onto its back, and the other one was tail slapping a great white or something.
Yes, that's it. That's the one.
So they were trying to drive it away, and depending on how much intelligence you ascribe to a large whale like that, maybe they kind of think of humans as sort of like baby whales.
I don't know.
So maybe that's something you'd see in the defense of a young humpback.
This woman is studies the humpback whales for like 20 years, and she has never ever even come close to having any kind of experience like this. She is completely flabbergasted, and now she's doing like a whole new study because she didn't know that was possible.
Okay.
I mean, the thing about intelligence, and this applies to, I would imagine, whales as much as to intergalactic or planetary civilizations throughout our galaxy, is just because a civilization or a species develops intelligence doesn't mean that they're really interested in bragging about it or finding galactic friends. They might think that's a very bad idea. If they had a history in their evolution of being preyed upon.
I was going to say if they were delicious.
Yeah.
Crunchy and good with ketchup, yeah.
Molest ye not dragons.
They might be very, very smart clams that have very good internet connections and play games with each other and don't want to talk to anybody else.
That's always possible, but don't you think that would be just a sub-factor of term 6?
Well, I mean, the question is how could you tell the difference? Earlier you were talking about.
Well, you can tell the difference because that type of civilization doesn't communicate with you, so you never see them.
Well, I think it comes, it brings into question: do we really understand what intelligence is? So when we're talking about aquatic life not being able to build radio telescopes, well, these whales that was a very intelligent and altruistic thing to do, and yet, they're swimming around. That they are mammals. They're not fish, as many people realize.
That's why it's worthwhile distinguishing intelligent life from intelligent life that chooses to build a civilization or build a technology.
Or technological life is another way to.
If you
shorthand
can,
for that.
how can a whale? It seems like a very intelligent thing to do, yet it is virtually impossible for whales with fins and stuff to build, any artificial thing,
But it's not difficult to imagine a counterfactual of a water-dwelling creature that could have the limbs that could manipulate its environment. It could do some very interesting things, as somebody said earlier. It might have even been you, Patrick, who said that earlier.
Yeah.
Oh,
maybe
octopi have limbs. Yeah.
Yeah.
Circling back to our rhetorical discussion here, I will fully concede that Oumuamua probably plays zero impact on term 6.
Okay. So
I'll concede that one.
what about term 7?
Well, that's the question. If we develop a better understanding of how much this population of interstellar asteroids actually interacts with the planets, I'm talking about
You mean smashing into planets? That's what you're talking about.
Sure.
No point in mixing words here. Compared to the huge population of comets and asteroids we already have.
Well, we're talking about, okay, so I think Chicxulub, which was thought to wipe out the dinosaurs, has been assumed to have a velocity of about 20 kilometers per second.
Yeah, that's well within the solar system.
Whereas Oumuamua at Earth orbit, I think it was more like 60 kilometers a second. So you take kinetic energy, v squared, that's 3 times more velocity. That's 9 times as much energy.
Yeah, but it's not near as massive as the Chicxulub.
These things are going to pack a lot more of a punch.
Yeah, but the thing is, the Chicxulub comet or asteroid, whatever it was, that's drawing from a much larger population.
Potentially.
No, it is. Or we would have seen a lot more of them. We know there are millions of asteroids, and we don't know how many comets there are, but there's probably billions of them.
In terms of the age of the solar system, we're still in the Chicxulub era. There's already been the late heavy bombardment. Our solar system is relatively clean and evolved and organized to some extent. We have Jupiter to thank largely for that. But, we're still in an era where something like a Chicxulub is, it's conceivable.
Right. Well, if comets we don't know about, but asteroids, I think we know all the ones we know, or very close to knowing all the ones that size or larger. That could intersect the Earth's orbit. We're close to that.
Okay. Well, I guess what I'm saying is that for term 7, if this population is significant to the effect where it strikes a portion of the life-containing planetary civilizations in our galaxy, then it could have an effect on 7. Again, directly.
For clarification, can you tell me what 7 is?
The length of time over which a civilization releases detectable signals.
Basically, the lifetime of the civilization that's willing to communicate with the rest of the universe.
Yeah, and that might be a very short window for everything that's made it up to 6.
Yeah, but we don't have any evidence there's ever been a civilization threatening collision with anything interstellar. So I mean, the probability is very low, which suggests to me that it would have a very minor effect on the 7th term, if any, at all.
Well, the point is we're not seeing most of these. That's part of
Yeah,
the
but
point.
we're not
This
seeing
is
them
the
because
first
they don't
one
come
we-
anywhere near us.
This is the first one we've seen.
too.
Now, if there's 10,000 of them, if there's 10,000 of them in the solar system at any one time, eventually, just through statistics, you're going to have some near misses, if not some actual hits.
Remember.
Well, we
too,
don't
that-
have any evidence of that, though.
Remember,
No, we
too,
don't have any evidence of that.
dinosaur killer asteroid may have well been the driver of the evolution that caused us to evolve into intelligent beings. So, for example,
Yeah,
the dinosaur
it may have been a factor. Yeah.
Well, it certainly was a factor for the adaptive radiation of mammals, and we live now in a world in which mammals are under the water, on the ground, in the sky, everywhere. So, it played a central role in that respect.
Yeah, and some of the primates are pretty cheeky and think they're smart.
So I guess then an interesting side note to this is that I'm kind of starting to wonder if Shoemaker-Levy 9 wasn't an object of this kind.
No, it wasn't. That's pretty well understood.
Well,
It was
The reason-
not an object of this kind in what way?
Well, you can trace back to.
you can only go so far. You can only trace that back so far. And the big question is, where did that object get fractured? And if there's some,
Well,
if there's
it got fractured by an earlier close encounter with Jupiter. So yeah, it was not interstellar.
Yeah, Shoemaker-Levy is a known comet. And in fact, I was out there with my little telescope at the time. And I saw some of the spots that it left on Jupiter.
Because it's a cometary body, it cannot be interstellar.
No, it's just that this particular one wasn't.
Okay,
Yeah,
how do we know that?
The trajectory was known. It was a
Well,
If there's no excess energy, then it's trapped. It's within the sun's gravitational sphere. It can't. It's not going to leave. It didn't come from somewhere else.
But you can do gravity capture. Not everything is a slingshot.
Yeah, but
that increases
the
your
physics of that is all really well understood, and no, it wasn't.
But looking at this in the larger picture, should we or should we make a distinction between bodies in the Oort cloud that can fall inward into the solar system and become comets that are of origin from the processes that built our solar system, and the other matter with which that cloud is in communication that is of interstellar derivation?
What do you mean
how
by
far
in
back can we
communication?
go?
I'm sorry, I don't understand.
Well, the Oort cloud is way out there,
Yeah.
almost a light year or two away.
Well, not quite that
So,
far, but pretty far. Yeah.
But it's going to have more interaction with matter from outside the solar system than the stuff that's closer in, inside the orbit of
almost zero. I mean, it could
Almost zero?
gravitationally, yes, it could interact, but not. It's not going to.
well. Remember,
The odds of a collision are extremely small.
No, I'm not saying a collision,
Right.
but some of more of the matter in the Oort cloud is going to be of interstellar derivation than the matter that's in the inner solar system.
Everything's of interstellar derivation if you go back far enough, but
Right.
no, I don't think this is different. This is stuff that where the sun is moving along in its orbit around the center of the galaxy, and there's driftwood out there. There's stuff, and every once in a while, some of it the sun moves towards it and it falls in, and because it's not really captured in any particular gravity well, it just finds us and just goes, and that's what Oumuamua was. It was the studies show that it's nothing exceptional about it. It was probably just moving along with us, and we just ran into it. It's not.
However, it should be pointed out that that's not entirely arbitrary, because it's thought that when our planetary system is passing through the center of the Milky Way's disk, we encounter more interstellar objects, and when we're a little bit outside the disk,
we don't get that
encounter
far
less.
out of it, though.
But there is a variation over some hundreds of thousands of years.
There could be
of our
a
position in the-
variation. I don't think we have a good handle on that.
No, we
'cause
don't.
We don't really know
I
what the
was-
population is.
I was going to point out something that Paul basically pointed out already. If you go back far enough, the fact is that the entire solar system is
Interstellar.
has been begat from a stellar explosion in the far off past.
Almost
Because
certainly,
it-
yeah. We're probably like we're just a piece of a previous supernova that just blew off a whole bunch of gas and dust, and
all of our metals and everything was born from a supernova. So
yeah, it might even be like the third generation.
Okay, Shoemaker-Levy was traced back. They think it was captured in Jupiter orbit in the early 70s, but could have happened as early as the mid 1960s.
Yeah,
So
we didn't have any observations of it, I think, before for like the 90s or something like that.
no, but it definitely doesn't say this was. I mean,
If it was interstellar,
when is the
it wouldn't have been
capture-
captured by Jupiter. It would have just gone rip right through it.
why?
Because
Doesn't that
it would have
depend on its
excess
incoming?
energy. It wouldn't have been able to capture it.
There's no way that it could have had a lower relative delta V.
Delta V? That's not
Yeah,
relevant. Delta V doesn't mean anything
of-
here.
a velocity relative to
No, it would
our
have
sun.
it would have come into Jupiter at a very high velocity and just whipped around it and gone back out.
Why does it have to come in at a high velocity?
Because it's from a because Jupiter's actually relatively low in the gravity well of the sun.
Yeah.
So if you're from an interstellar position, you have a very
If I'm
high.
coming from interstellar, why do I have to be coming at a high speed relative to the sun
just
or
by the
Jupiter or
nature-
whatever?
It's
by the nature of the
energy.
fact-
It's conservation of energy.
by
This
the
is
simple
high
fact-
school physics.
by the simple fact, Buck, that if this thing came from somewhere else, it would have
Yeah.
had to have an extremely high energy velocity in order to escape from wherever it came from in the first place,
Relative to that system.
relative to something that fell in from the
Yeah.
Oort cloud or some other.
Well, even the Oort cloud comets have a high energy, which is why they come in at a very high velocity into the interstellar system. And but there's lots of comets that are not Oort cloud comets. They're just sort of
Okay, well,
comet
I
comets.
misspoke.
Yeah.
The point is that, like Paul says, if it came from from another star, it would have had to have a very high energy to begin with. It didn't just fall in from
Relative to
our
us.
neighbors.
Yeah, I was thinking
You mean like-
everything in the solar system has a negative total energy. If you're outside the solar system, you have zero. So you have to get to that negative energy. You have to increase your kinetic energy to still say it's zero conservation. So you have the kinetic energy.
What's
has to go
negative
away.
energy? What's negative energy?
Well, the
look like?
potential energy in gravitational well, the way we model it is negative. It's negative energy.
Oh, because if it's above escape velocity. For whatever. That's negative energy?
If you model the total energy in a gravity well, it's negative. If you're just going around, let's say, in a circular orbit around the sun, you're in a negative total energy. It's just it's a way of bookkeeping. It's not.
Okay, so how do you what numbers are you plugging in that make it a negative?
Well, you plug in the potential energy from the gravitational well, which is negative, and then the kinetic energy is positive. This is high school physics. I don't want to go over it again, but
I spent a lot of focused attention in high school physics, and I don't recall us ever describing like the kinetic energy.
well, you
of
go
the
in any
Earth
textbook,
as
you'll
negative.
understand how orbital energy is described in celestial mechanics. It's not controversial, but
I'm not saying it's controversial or not. I'm saying I don't understand it. Is there what numbers do you plug in to get like a negative energy? I'm not.
well, there's a minus sign in front of the gravitational potential energy. It's minus mu
As
over,
if
minus
like
mu
a
over
planet
r.
were to fall into the sun?
It doesn't have to fall into the sun. No, it can be in orbit around the sun.
Okay.
That's
It's just-
I just stated a fact. It's not. I mean,
Basically, Buck, I don't know how much you remember about the conservation energy, but as you gain velocity in a gravity well, you lose potential energy. There's a trade-off there, and the total amount of energy is conserved at any one point, but you're basically, as you're losing potential energy, you're gaining velocity or kinetic energy.
Right. Okay. I'm totally on board with that.
Yeah.
That's consistent with what I remember from high school physics.
I mean, you could define it differently so that everything was positive, but it'd still be the same result. But it would mathematically be very, very clumsy. So what we have is we define energy inside the gravity well for objects that are captured by the sun or by any central body as being negative. And then if you're out an infinite distance from that body and not moving at all relative to it, your energy is 0. And then you start to come in towards the body, pulled by the gravity, right? Your energy is still 0. You're on what they call a parabolic trajectory, and your speed has to increase to maintain the conservation of energy.
Like angular momentum relative to the center of gravity.
Well, it's not angular momentum conservation; it's energy conservation.
Okay, so we're not talking about energy in terms of momentum?
No,
it's something else.
No, not really. I mean, you can write the equations down in terms of momentum, but no, think of just simple velocity. Okay.
Okay.
If I mess out, there energy of 0 and the gravity's pulling towards itself, right? The central body's pulling. I'm way out. Infinite. So let's say effectively infinite radius.
Okay.
In this universe, where there's only one central body and me, right? I have essentially no mass compared to it. It's going to pull me towards it, right? And my velocity has to increase because the energy is conserved. So I had 0 energy out of that infinite radius. I come towards it. I still have 0 energy. My negative energy is as I'm getting closer to the body, my gravitational potential energy increases, gets more negative. So it decreases actually. So as I come closer to the body, my kinetic energy has to increase. And so I go faster and faster.
Yes.
And not directly related to angular momentum at all. You could come straight towards it with 0 angular momentum if you hit the body, at that point.
Right. I was only bringing up that in response to the use of the word orbit.
Yeah. Well, orbit. If you're in orbit, right? Then you have a stable exchange between kinetic and potential energy, and no orbit is perfectly circular, so you'll have some coming and going out all the time. So
they're elliptical, right?
All real orbits are elliptical, yes, even if only very slightly.
Yeah, with other planets and whatnot.
Well, I mean, the Earth's eccentricity, going by memory here, is about 0.03. I'm sure that's not quite exactly right, but the eccentricity of Mars is much higher. So it varies from planet to planet, and some asteroids are highly elliptical. Comets are extremely elliptical. Or cloud comets are almost on what they call parabolic trajectories. That is, they're almost an eccentricity of nearly equal to 1. If it's greater than 1, it came from outside the solar system.
Okay.
Hey, Paul, I want to. I realize it's unlikely that Shoemaker Living 9 was an interstellar object. I don't really have a dog in the fight. I'm shooting out ideas here. But it's not, you can't rule it out from what we've observed about Shoemaker Livy 9.
I think you can roll it out.
It's not one of these.
I think it can roll it out. Yeah, it can roll it out.
don't restrict his freedom of speech.
He can say whatever he wants, but I mean, I think you,
no, I was talking to him.
he can rule it out.
Don't tell him he can't rule it out.
I think there are scenarios under which it would be possible. I'm not daunted at all.
Yeah, when you say something's impossible, I think the bar of evidence it's raised.
Well,
I think
when you
strong
roll something
justification.
out, you're saying basically the probability is so low it's not worth thinking about. And I think that's the case here.
Well, I think it's the case
in many other situations.
Well, let me draw your attention back to a couple things, and that is, one is that Oumuamua spectroscopically looks exactly like the kind of stuff that Jupiter likes to scatter and trap. And so Jupiter has this sort of spectroscopic class of object at its Lagrange points, L4 and 5. They're a distinct cluster spectroscopically. They don't look like reddish Oort clouds or, icy moons of Neptune or anything. They're kind of their own beast. So conceivably, the kind of stuff that Jupiter would scatter, and there's a large population of this stuff, so Jupiter is going to see quite a number of these things. That if there are 10,000 of them inside the orbit of Neptune at any one time, Jupiter is going to be seeing these on a constant basis.
But they're not going to get trapped in Jupiter L4, L5 at all. That's not even possible.
Well,
they have way too much. They have way too much energy.
You're assuming energy conservation as opposed to a gravity desist.
Energy conservation and gravity are under gravity is still valid.
Yeah, right. But the thing is that kinetic energy gets conserved into other things like little explodey bits.
No, little explodey bits are a completely different story. If you collide with Jupiter, that's fine, but then you're not going to become a Trojan asteroid. To become a Trojan asteroid, you have to sort of drift into that big area with low velocity. It's completely different dynamics.
Okay. I mean, there's a difference between being impossible and inconceivable. And
I agree. Inconceivable is much more of a hard constraint than impossible. What I'm saying is ridiculously improbable.
So where does that leave us? What have we learned? What have we taught ourselves about Oumuamua tonight?
Well, I think what we taught ourselves is that the research that the professionals are doing needs to continue, and they will. And there's still a lot of work going on right now, and probably this year we'll get a lot of new papers out. And we learned. I really hope we'll catch another one of these things in the next few years. The good news is that the astronomical surveys that are out there are getting better and better all the time.
Well, how do we know it wasn't an interstellar war and aliens are throwing asteroids at each other and one got away from it?
Well, Patrick Festa told me that, so I don't believe it for a second.
I just throw that out there.
Well, I'm sure Richard Hoagland thinks that, but
any Transformer fans? It's actually the Autobots. It's the Autobots mothership. Sorry.
Well, my first thought, being an old guy, was Rendezvous with Rama, going back to my youth, but because it was almost the first few days of it was almost like the Rama scenario. We spotted this thing, and it's long and skinny, and it's entering our solar system. And we got.
I was thinking about rendezvous with Rama when looking at the Drake equation in terms of communication. Does that artifact from Arthur C. Clarke qualify as something that we might detect? And not really.
No, I think it does. I think it does. I think the Drake equation is still valid, but SETI should extend itself to SETA, which is search for extraterrestrial artifacts. And I think that's a very serious issue that should be addressed.
Well, I think we've already,
SETI
has already done that pretty absorbed that, by the GHAT survey, which was a survey for infrared sources that would be something like a Dyson sphere, which we discussed last time or the time before.
Yeah, and the same guy that led that survey, Jason Wright, has also written a paper about looking for artifacts in our solar system.
Yeah, he's written a lot of stuff on Tabby Star as well.
Yeah, Jason's a really leading SETI thinker, and he's also a totally legit astronomer in his own right. And so if we did find, now I don't think Oumuamua is artificial, but if we did find something that had the earmarks of an artificial object, let's say it came into our solar system and its orientation changed in a controlled way that we could observe, that would be astonishing, and it would probably also be pretty strong evidence of artificiality, because natural asteroids don't, they just tumble. So that would be a communication from another star system. Yes, it would, if nothing else, just one bit. It says, "We are here," or we are not from here. We're not from here, I should say. Who we are, you have some more work to do to find out. But that's and back in the 1960s, a very serious scientist named Ronald Bracewell wrote a whole paper about that called, those things have been called Bracewell Probes.
Yeah.
And Rendezvous with Rama was basically about a Bracewell probe.
Well, actually, no, a Bracewell probe is intended to communicate, and it's pretty clear from the Rama story that it's not intended to communicate anything.
I did say basically, right? Yeah, okay. Yeah. Well, Bracewell scenario was that it would come into our solar system, keep an eye on us for a very long time, and then at some point unleash a torrent of information about who they were, right?
Well, the motivation behind the Bracewell probe idea is the frequent criticism of SETI that you can't hold a conversation when it takes 1,000 years for a message to transfer. But if you had a rudimentary artificial intelligence installed in a robotic probe, that it could go to another solar system, it could wait until it got intelligence signals from someplace, and then once the civilization at the other end reached a level of communication, then it could communicate by proxy for the civilization that sent it.
Yeah.
So you get some in a universe in which you believe that interstellar travel is impossible for biological beings like ourselves, you can still get real-time communication without having to deal with the SETI delay. So it's important to understand that that's a motivation behind the Bracewell probe idea.
Yeah, and I think it's a perfectly reasonable.
It is
conjecture. I wouldn't say a hypothesis, but
we're nearly at a level of technology where we could build a Bracewell probe now.
Yeah,
although it take a long time to get us.
We're probably a generation or two away from that. Yeah.
Yes.
And we don't know where we'd send it, but if we could find a Earth-like planet somewhere that we're pretty sure hasn't developed a civilization yet, we could send it there.
We'll have a good Earth twin before we can build a good Bracewell probe.
I think that's pretty likely. Yeah.
I mean, we'll have that within 20 or 30 years, no question. I mean,
we might have it in 10 years.
Right.
We might have it next week, but less likely. But anyway, I'm going to wrap this up, and because we have been, let me see, how long have we been recording? We've been recording for almost 2 hours. Not that there's anything wrong with that, as Jerry Seinfeld would say. So anyway, anybody want to get in? Have any last word? Just pipe up now, and then we'll say goodnight.
I'm looking forward to listening to some Skeptic's Guide to Conspiracies.
Yeah. Mike Bohler, what's next? What's next in Skeptic's Guide to Conspiracy?
Well, I'm still working on I'm doing a new, taking stuff out of the news. So there seems to be this conspiracy that's trying to resurrect Pizzagate and make it into something bigger. Apparently, there's a guy that's on 4chan who claims to be a CIA agent with Q clearance.
Oh, well, he's on 4chan. It must be true then.
Yeah. I when I first saw that, and I go, wait a minute. There was an episode of Archer where they end up in Area 51. And
Yeah,
Archer's-
Nellis. It's a two-parter.
Oh, it was a one part. The Nellis one was.
Yeah, I think you're right.
Yeah.
Yep, my bad.
Yeah, because they get off the plane and he goes, wait a minute, I got Q clearance. And then he gives the code. And I'm like, does the CIA, I wanted to know if the CIA really used Q code. Well, they don't. Actually, from what I could find, the only agency that uses Q clearance is the Department of Energy.
Ah, like a nuclear weapon thing.
Right.
Yeah.
And so right off the bat, I knew this guy's full of crap.
Can I pull a shameless plug before you stop recording?
Go for it.
Go ahead, Patrick. Shameless plug now.
Okay. Well, the short story from Long is that YouTube had suddenly slapped us YouTube channel monetized channel owners with a new rule, and that is we have to have 1,000 subscribers in order to keep our monetization. So for the last couple of days, I've been pulling this subscribe-a-thon thing, where I'm trying to get up to 1,000 subscribers and above before the February 20th deadline. So if you catch this audio podcast and it's before February 20th, please visit my channel and subscribe so that I might keep my monetization.
Oh, well, all right. Let's
Give
see.
us a link. We need a link.
Oh, well, yeah, just send me a link, Patrick. Okay. John, any last word?
Not that I can think of at the moment.
Okay, well, thanks for being a new panelist. We appreciate that. It's good to have some fresh voices on the show. Nick, anything?
Nothing more at the moment. Thanks for having me on again.
Okay. Did I get everybody? Buck, you said your thing. Okay. So anyway, this is the Unseen Podcast. Go to unseenpodcast.com for more information. Our email is unseenpodcast@gmail.com. And we also have a Patreon campaign. If you want to help defray the cost of this podcast, I would not recommend pledging more than, say, $1 a month or so, because let's face it, there are other charities that are more deserving of your money. But just drop a little extra change on us if you have it. We will be back next Friday, with another episode. We usually have them 2 weeks apart, but because of scheduling conflicts, we're going to have one next week, and then we're going to have one like in 2 weeks after that, or maybe 3 weeks. I can't remember. If you'd like to be on the show, by all means, go to unseenpodcast.com, and there's a FAQ there. You can see how you can get on a panel. Essentially, anyone can be on the panel. And the topic that we will talk about is largely up to you. So you come in, you engage with the discussion thread, and we'll talk about what we want to talk about. And there are a few times when we have a special guest on, and then obviously the discussion is focused on that special guest's level of expertise. Adam Synergy Smith is working on one for us very soon. I'm also hoping to get a couple other people on. I won't mention their names yet because they haven't said yes yet. So we'll work on that sometime the next few weeks, or maybe in the spring we'll have some more guests. So it's getting quite late. So I'd like to say thank you and good night to Buckfield.
Thank you. Thanks for having me on. Very interesting.
Jon Eckberg.
Good night, Paul. Good night, everyone.
And Mike Bohler.
Thanks for having me on, and good night, everyone.
And Nick Nielsen.
Thanks, Paul.
And Patrick Festa.
Thanks for having me on the spur of the moment.
Okay, thanks everybody, all 5 panelists, and especially our new panelist, Jon Eckberg. And we will see you in 1 week. This has been episode 86 of the Unseen Podcast. Now listen to some DJ Spooky, and good night.